So, today we're going to continue entity relationship model discussions. We talked briefly about how these relationship sets have a degree, which is how many entity sets are participating in a particular relationship set. Here's a degree 3 relationship set called works on. Right? We have employees, jobs, and branches. And so you could say, I am a bank teller at this branch, and I am a mortgage financer at this other branch, and I am a, what else could you be? You could be a manager at a third branch. And these kinds of situations are able to be modeled with this kind of a design. Okay? So employees are assigned jobs at various branches. Notice, no arrows. So this is a many-to-many mapping. And so we're allowed any combination of employee, like Jenkins can be that manager at one branch, and he can be a loan officer in another branch. That's okay. He could even be a loan officer at the same branch and a manager at the same branch. Any combination of entities from these three entity sets. Remember, each relationship can only appear once, but there can be multiple relationships involving the same entities. So Jenkins could be a loan officer. He could be a manager as well. No problem, right? Everybody believe that? That's the way this is spec'd. You can specify some mapping cardinalities. Basically, we allow one arrow on these links. We do not allow more than one arrow because of brain damage. And I'm not really embarrassed to say it. It's complicated anyway, so why would we do it? And I honestly have never found a situation where this became a real problem. So each combination of employee and branch can only be associated with one job. So what we're now saying is that Jenkins, if he's working at the Brooklyn branch, he's only allowed to have one job at the Brooklyn branch. So maybe it's loan officer. He's not allowed to also be a manager. He can only be a loan officer. But if he also works at, I'm trying to remember another one, a Perry Ridge branch, well, at the Perry Ridge branch, he could be a manager. That would be okay. But we're saying that a pair of employee and branch can only correspond to one job. That's what that arrow means here. Okay? All right, so that's the idea. The reason why we allow only one arrow, let's say not only one arrow, but at most one arrow, is because there's brain damage in the definitions for how we would understand multiple arrows. There have been at least two meanings defined, and I think that one of them at least is dumb, and the other one makes more sense, but since these multiple meanings are out there, we go ahead and just constrain ourselves to only one arrow. So let's say that we have this situation. Entity sets A, B, C, D. They all have a relationship set R. I like that picture way better than the generic version because it's like more difficult to understand. So A1 through AN, and then we have no arrows on some of them, and the others we have arrows. Okay? More than one of them, too. So here's the first meaning. Basically, we take the entities from the entity sets on the non-arrow side, and we say that a set of entities from those can map to at most one entity in the side with all the arrows. Okay, so a particular combination of entities in A1 through AI can be associated with at most one set of entities in AI plus 1 through AN. Using our simpler picture, what we're saying is like a combination of A and B can only map to one specific combination in C and D. That combination from A and B cannot map to another combination in C and D if we have these arrows. It's a constraint. We're constraining what we're allowing to be represented. So primary key of R is a union of the primary keys on the sides without arrows. Okay? So in this case for R, we'd have a primary key taken from A and B, okay, which I denote as lowercase a and lowercase b, if you'll forgive the imprecision here. We're just saying that whatever A's primary key is plus B's primary key, that's the primary key of the relationship set. Okay? So then, knowing that, we can go through and start saying, well, what kinds of relationships could we represent? So here's an example of a relationship instance. A1 and B2, C3 and D5 are all related to each other somehow. Yeah, I don't know what we're modeling, but this is just an example. Then we have another relationship instance. A3 and B4 and C3 and D2 are all related. Okay? Then we have a third one. A3, B4, C6, D9. Is this allowed? Look at the primary key on that relationship set, and it includes A and B together. So in this case, A3 and B4 already appear. We're not allowed to associate them with the second pair of entities from C and D. We can only have that represented once. So that one's not allowed, and so forth. Okay? Does everybody get it? I mean, it's a pretty straightforward concept. There's nothing really fancy about it, and I like it. It's simple. Now, have I ever had a reason to use this in real life? Absolutely not. So, ternary relationship sets with more than one arrow is not really useful. And even with one arrow, it's kind of nice, but you don't run into needs for it very often. In fact, I believe that you will find a benefit for it on assignment 5. I tried at least to come up with an assignment where you could use it, but they're pretty dang uncommon. Okay, here's the insane meaning. So we have more than one arrow on our degree greater than 2 relationship set. What we're saying is, look at each arrow individually. And so you have an arrow pointing to a particular entity set. All the other entity sets in the relationship set are considered to, be distinct when it comes to entities in that one particular entity set. So for each entity set AK, which is an entity set with an arrow to it, a particular combination of entities from all the other entity sets can be associated with at most one entity in AK. Which means, let me see if I can see, it's just ridiculous. Let me just show you. We have our simple example, A, B, C, D are entity sets, and we have this one relationship set R. We have 2 arrows. So what that means is that we have one constraint that a triplet of entities from A, B, and D can only correspond to one entity in C. And there's another arrow, so we have another triplet from A, B, and C that can only correspond to one entity in D. There's 2 different constraints being represented here. So if I said the last one was simple and made sense, but I can't think of a reason to use it, this one is complicated and doesn't make sense, and I still can't think of a reason to use it. So no benefit, right? Why would I even use this? But just to give you an illustration, so we have A1, B2, C3, D5. So again, we have 4 entities that are associated with each other. A3, B4, C3, D2. Is this one allowed? So ABC, yeah, we're okay there. Different triplet. ABD, another triplet, so we're okay. What about this one? A1, B2, C1, D4. That's okay, right? Because A1, B2, C1 doesn't appear anywhere else, and A1, B2, D4 doesn't appear anywhere else. A3, B4, C5, D7. Again, the ABC triplet doesn't appear anywhere else, and the ABD triplet doesn't appear anywhere else. Okay. So here's another one. A1, B2, C3, D6. So we look at the ABC triplet. Oh, wait, that appears somewhere else. The ABD triplet doesn't appear anywhere else, but we've violated one of the candidate keys, so that one's not allowed. A3, B4, C8, D2. Well, that one also appears somewhere else, so ABD appears in that case. ABC is okay. So there we go. That's a simple example. Now, the thing that I want to point out here is that 4 of those would be disallowed by the first meaning. 2 of them are disallowed by the second meaning. So you can see that these are pretty significantly different constraints. Nasty. And so we say we're going to just exclude all of this by saying we only have one arrow. And that's the one that actually seems reasonably practical anyway, so why should we even allow the other ones at all? Okay? So if you find yourself on a relationship set with a degree greater than 2, and you're finding yourself wanting to put multiple arrows on it, stop yourself. You may be doing it wrong. Okay. All right, let me ask you this. Any questions? Like, that was a side trip for sure. I mean, I just told you something that, well, I guess it was good because you got to see the reasons why we don't like this. But still, it's something that you won't ever run into. Okay. There are usually the cases that you are not going to use ternary relationship sets either. They tend to be pretty dang rare. Okay? Most of the time you're going to have degree 2 relationship sets. In fact, a lot of tools only allow you to have degree 2 relationship sets. So it's like, why would I even allow degree 3 relationship sets anyway? So let's say that we have this configuration. So again, we have entity sets A, B, and C, relationship set R. We could try taking this ternary relationship set and replacing it with another entity set and 3 binary relationship sets. Something like this. It's an idea, right? And so if we had a relationship instance, AI, BI, CI, and we took this, we could map it to some kind of relationships in this new configuration. Notice E is a separate entity set that sort of represents that there's a relationship between the A, B, and C values. So we have EI, AI, EI, BI, EI, CI, right? Everybody got that? Now the question is this actually the same as the ternary relationship set? Or is it a little bit different? And it turns out that it's actually rather significantly different. And I'll show you a few ways in which this is different. Let's say that we want to represent a specific relationship between entities A5, B1, and C2. Okay, no biggie. The question is, how many relationship instances can we have between A5, B1, and C2? Okay. Well, let's say we're taking R. Okay, A, B, and C related through R. Well, if we want to represent A5, B1, and C2, we can represent that once, because remember, it's called a relationship set, right? So that's cool. Okay, so A5, B1, C2, that's no biggie. Ternary relationship set, we're good. Our alternate approach, how many times can we represent that particular relationship instance in the second version? Well, it turns out that we can't really constrain this to mean the same thing as the ternary relationship set. You can get close. You can get really close, actually. So we could create many relationships. We could have A5, E1, B1, E1, C2, E1. So now we've represented that. But then we have A5, E2, B1, E2, C2, E2. We could just keep going, right? We could just keep throwing as many. So you'll notice that this is a relationship multi-set, not a relationship set. Okay? And that can have some pretty profound impacts. You know, you all know this now from writing SQL and doing joins across things and finding stuff represented more than once. Because maybe along the way something isn't a primary key and then suddenly you have multiple instances of it. So we would run into that problem with this representation. Okay? There's just no way to represent that. If you think about the issue here, I don't know if I actually say this on the slide. Yeah, you can't constrain it in the exact same ways. I'll throw this up here and just show you. The reason why you can constrain R to represent only ternary relationships and you can represent it as just a set of ternary relationships is that you have the keys of A, B, and C all together in one place. They're all in R. Like if you translated this in the relational model schema, you get the primary key of A, the primary key of B, the primary key of C. You can enforce a constraint on how those things appear together. Think about the corresponding question for the second model. Is there any place where the primary key of A and the primary key of B and the primary key of C all appear together in one thing? Well, there really isn't. Because, you know, A, B, and C will be by themselves, E will be by itself, E does not have the primary keys of A, B, or C in them at all. Why would it? It's an entity set. RA contains the keys of A and E, RB contains the keys of E and B, and RC contains the keys of E and C. There's no way to get the primary keys of A, B, and C together to impose a constraint. Okay? That's why the ternary relationship set is special. You can represent special things with it. Like if you have an arrow on one of those lines coming out of R. If you have an arrow coming out of one of the lines on R, there is no way to constrain this second version to enforce the same constraint. There's no way to do that. Okay? That's just one of the realities of this situation. You can try, but you will fail. Okay? So anyway, that's an important detail to keep in mind. So you have situations where you have to make decisions. Do I want to do this as a binary relationship set, or do I want to do it as a ternary relationship set? Here's an example. Office equipment. We all love office equipment. Great for making photocopies. So you have a ternary relationship set between departments that machines are used by, the machine itself, like the photocopier on the third floor, and the vendor who is responsible for taking care of said photocopier. Usually when you have a machine like that, it'll be an expensive machine. It's like super expensive. And a lot of times, because it's got all these features and stuff, like most of the copiers now can scan, print, there'll be document servers, so they'll have an Ethernet connection, so you can put them on the network and you can scan and then download, or scan and then email, all this stuff that you can do. And they break. Because somebody tries to feed cardstock through the paper feed or something like that, or they try to scan a book and the book gets sucked in or something. So all these horrible things that could happen. So the machine breaks, and then we got to have somebody come fix it. And so that's the role of the vendor. They come and fix the machine when it's broken. Or they install the duplexer when we're like, hey, we don't have duplexing capability. So what if you don't know a vendor for a machine? Maybe you have a little printer and you're like, well, this printer doesn't really require a vendor, so I don't have a vendor for this. Well, so then you have to ask yourself, does it make sense to have a ternary relationship between all of these things, or does it make sense to have a couple of binary relationships? Okay? Because if you have a ternary relationship, then you're going to have some relationship instances where the vendor information is unknown or unspecified. We know the value for that. And so we'll have to have null in that relationship instance. Not ideal. Not the end of the world, but definitely not ideal. Okay? If we had multiple binary relationships, like a relationship between departments and machines, okay, yeah, this is still the printer that the department uses. But then there would just be no relationship between that machine and the vendors. Just leave it out. Okay? Everybody see that? So sometimes it can make more sense to have binary relationships when some parts of the relationship instances may be missing. Okay? So yeah, we'll use binary relationships in those cases. All right, any questions about that? Now, here's another one that I personally like because I've had lots of experience with it. When you have a homework submission, it is a relationship between three different things. You have an assignment that the submission is for, you have a student that submitted it, and then you have the submission data itself. That actually makes a lot of sense to have a ternary relationship because you ask yourself, does it make sense for any part of this to be missing? Does it make sense to have a submission without an assignment? Well, no, it does not. Right? Does it make sense to have a submission without a student? Definitely not again. Same thing. Does it make sense to have like a student and an assignment without a submission? Nope. I mean, we should represent that those things are not present yet because a student hasn't turned anything in, but that's a great example of something that you could represent as a ternary relationship set. Okay? Does CS121 do this? Well, it turns out the answer is no on that one. The reason why CS121 doesn't do that is because the software that we use doesn't understand ternary relationships. It only understands binary relationships. So I had to come up with an equivalent way of doing that. Okay. But anyway, this is an example where you could definitely do it as ternary relationships. Are there other ways? Well, like I said, there definitely are, because sometimes you have to. That's what I ended up having to do. And so here's another example where we've taken the homework submission and we've figured out a way of relating it to both students and assignments. Yes, the student submits this thing, and the thing is for this assignment. Okay? Is this the same exact abstraction as on the previous slide? It's not. But that's okay. It's still adequate for modeling our needs. Now you'll notice that we have sub-ID because part of the constraint was we had to support multiple submissions from a given student for the same assignment. Okay? That was just a rule because that's how we work in some of our programming classes. You can resubmit for a better grade. Okay? You also notice that we have constraints on here. Does it make sense to have a submission without a student? Well, no, we already talked about that. So we have total participation on the submission side of that relationship. Same thing on the other side. Does it make sense for a submission without an assignment? No. So we have total participation constraint on that relationship set as well. You can see we have a single arrow because each submission should be for one assignment, and each submission should be for one student. You can see that we don't support teams in this schema, right? If we wanted to change this to allow teams of students to submit, we could get rid of the arrow on the student side so that a submission could come from n students instead of just one. Okay, does it make sense to everybody? So this is pretty valuable kind of exercise to go through and figuring out what are the differences, what are the similarities, what constraints do I need to make this make sense? And honestly, in the ternary relationship set, a lot of that stuff was kind of implicit in the design. But now we have to be explicit about it because binary relationship sets are less constrained than ternary relationship sets can be. Okay? Any questions? Please don't ever design a homework submission system. It sucks the soul out of you. So it's pretty boring. Okay. Now you might look at this and say, hey, that looks a lot like weak entity sets. And Donnie really likes weak entity sets, so yes, this is all true. We could go ahead and redesign this to be a weak entity set where submission just has a version. Like the first submission is version 0, because that's how we do in CS. Although in databases we'd have to count from 1, because in a lot of database contexts we count from 1. So maybe we have submission version 1, submission version 2, and obviously the version numbers are not unique, but it is a uniqueifier, and so we could go ahead and combine that with the combination of username and short name, and then the version would be unique. So we can say that's a discriminator, and so we'll go ahead and make that a weak entity set. And notice that we have 2 identifying entity sets in this case. Okay. So primary key for submission. Well, we talked about this last time. Remember, the discriminator, we also call it a partial key, because it isn't a key by itself. Weak entities derive their identity from the strong entities that they, through the identifying relationships. So in this case, the primary key would be username, short name, and version. The combination of those 3 things together would be the primary key. All right? This would work as well. Okay. Is this what CS-man does? No, CS-man doesn't do this either because, again, the library doesn't support weak entity sets. Shucks, right? So it uses the one on the previous slide. That's all I could do. All right, let's see. Yeah, sometimes ternary relationships are best, especially when you know all the entity sets that are participating in that relationship set. Like there has to be an entity from each one of those. You don't have any missing entities. That's really good. And like I said, that's the only way to represent certain constraints. I'm pretty sure that you'll find this on assignment 5. I have to look at the solution set to be sure. But I'm pretty sure when I designed that problem that was one of the fun characteristics of it. So the bank jobs example, yeah, each employee branch pair can have only one job. It is not possible to construct a collection of binary relationship sets that can impose this constraint. It is not possible. And yeah, like I say on the slide, there's a reason. The simple version of the reason is that there's no way to get employee ID, title, and branch name into a single table to enforce the constraint. If you switch to binary relationship sets, well, no longer will the employee ID, title, branch name, triple actually all be in the same table for you to enforce a constraint on them. Okay? Questions? Alrighty, so that's that. I think that's enough beating ternary relationship sets to death. Now, if we're going to use this entity relationship model, we do need a way of converting diagrams into an implementation schema. So the whole reason why we like the ER model is that it becomes very straightforward to do that. Like I said, there's big overlaps between that and the relational model. Biggest difference is composite attributes. Remember, that wasn't allowed by the relational model. And then we also had multi-valued attributes, and those also weren't allowed in the relational model. So what do we do about those? 3 components of the conversion process. Schema of the relation itself, primary key on the relation, foreign key, references to other relations. There's also another step which I'm not including here, which is, hey, what about candidate keys, other candidate keys? Those need to be there too. Foreign key references become pretty important when you start talking about relationship sets. So yeah, strong entity set E with attributes A1 through AN. So, strong entity set. Why is it called a strong entity set? Remember, we have weak entity sets. Weak entity sets don't have a sense of identity, at least all their own. Strong entity sets do. So strong entity sets are super easy to translate into the relational model. We just make a relation with all those attributes, right? Just plop it down. Or if you want to talk SQL, you just make a table with all those columns, right? The proper corresponding domains, all of that kind of stuff. Okay, so relation schema with the same name E and the same attributes. The primary key is just what the primary key of the entity set is. Okay, so some subset of those will be a primary key. You just go ahead and enforce that as a primary key. If it doesn't specify a primary key, which is possible, then you're saying that all the attributes together are necessary. Then you go ahead and just make a primary key that enforces that all the attributes are part of the key. And what about foreign keys? Well, it's a strong entity set. It doesn't depend on anyone else, so it doesn't need any foreign keys to anything else at all. Okay, so that's a strong entity set. Every entity would correspond to a tuple. All right, that's what I said at the beginning. Entity sets correspond to tables. Entities, entity instances, if you will, correspond to tuples in the table. All right, so geocache location, latitude, longitude, description, last visit. I mean, how easy can you get, right? Turns into this relation schema. Yeah, that's it. Any questions? It's like, that's the easiest one. Customers and loans. So customer and loan. We're going to start with customer and loan. We just get to relations. And it's very straightforward to carry this down into the SQL implementation language. Right? Okay, so that one's easy enough. What about the relationship sets? Well, this is where, remember that relationship instances derive their identity from the participating entity instances. And because of that, the relationship set has to include the primary key attributes of the participating entity sets. So, A1 through AM is the union of all the participating entity sets' primary key attributes. And if you have any descriptive attributes, then you plop those on the end as well. So the relational model schema for R becomes this. All the primary key attributes of the participating entity sets, and then any descriptive attributes are thrown in there as well. Okay. Now, of course, the primary key attributes may form a candidate key, but they may not. We only know that they form a super key. And so we have to look at the mapping cardinality of R to figure out what the key or keys should be. All right. So let's say we have binary relationship sets, because those are easy to reason about. I'll give you a secret. anything that's part of the many is going to be part of the relationship set's primary key. If it's many to many, all of the participating entity set's primary key attributes are part of that one primary key. So many to many mapping, we have the union of all the entity set primary keys. Primary key of A union with primary key of B. If it's a one-to-one mapping, there is no many side. Well, if it's a one-to-one mapping, then the primary key of A could be a candidate key, and it is. Primary key of B is a candidate key. So we need to enforce both of those candidate keys. Okay. That's a one-to-one mapping. If it's many to one, then we have to do our little thinking thing and try to figure out what makes sense. Well, remember that many to one means that each thing on the many side can go to one thing on the one side. So the things on the many side are the values whose primary key value can only appear once. So again, the many side is part of the primary key. Okay? So relationship R between A and B, one-to-many mapping with B on the many side. Schema will still contain the primary key attributes from both sides. It has to. But then primary key of B is the primary key of R. It's on the many side. Those values can only appear once. Okay? Let me see. I think I have some examples. Oh yeah, the other thing is that relationship sets have to have foreign keys because they're relating things from entity sets. Okay, again, think about customer and loan and borrower. Borrower is associating customers and loans. So we have to have foreign keys. Relationship sets are going to generate foreign key references. So each entity set EI participating in R's implementation schema has a foreign key to EI's primary key attributes. Okay. Now, unfortunately, remember, I told you back in week whatever, when we were going through the first week of material, that the relational model doesn't have a way of indicating foreign keys. How irritating. So you'll have to make notes about this. I guess I'm a little sorry. It is a drag, and it's, I only require you to do it once, I think. But when you go through the process on assignment 5, you'll translate your ER diagram into a relational model schema, and then you'll turn it into SQL. When you go to the relational model schema, you'll have to write out, here are my foreign keys. And the reason you have to write it out is because there's no notation for it in the relational model, which is too bad. Okay? But anyway, you have to make sure you include those things so that you can actually put them into the data definition. All right, any questions about this? Okay. So relation schema for borrower. Well, we can just go ahead and look at this. Remember, relationship instances in borrower are identified by the participating entity's primary key values. So customer ID and loan ID have to be in the schema for borrower. We also have access date. So access date has to be in borrower as well. So that's pretty easy. And then you look at the mapping cardinality and you say, well, borrower is many to many. Since any loan can appear multiple times and any customer can appear multiple times, both of those attributes together have to be part of the key for borrower. Okay? So that's why we end up with the design that we have. Does that make sense? Are there any questions about any of this? You'll get to practice this. Straightforward, right? Here's a fun one. So what do we do in situations like this where we have an entity set related to itself? Well, this is where we have to use the roles so that we can distinguish between sides of the relationship set. So we have worker and manager. We can't just make a schema for works for that's employee ID, comma, employee ID. And so you can incorporate the role names somehow into the relationship set's attribute names. You can see two options, manager employee ID, worker employee ID. I personally like that one a lot because it's easy to generate mechanically through a program, but it's also not particularly helpful if you're trying to handwrite this stuff. So manager ID, employee ID tends to be far more widely preferred. Okay? Any questions? All right, so relation schema for employee. So notice, we're going to ignore phone number and the number of reports. Typically, remember, do you guys remember what the parentheses mean? It means it's a derived attribute. It means you have to compute it from somewhere. So obviously, if you're going to do a derived attribute, it's not really possible in SQL to do that as part of a create table statement. The way that we would do that is with a create view statement. You're all familiar with how to do views. That's literally what you would do for supporting something like number of reports. You would make like an employee underscore base, do your junk, and then create view employee as, and then select junk from places and go ahead and do that. That's how you would have to support a derived attribute. Multi-valued attribute. We haven't talked about that yet. So that's still something that we have to figure out as well. Okay. So relation schema for employee entity set, employee ID, and name. Relation schema for works for. Well, notice it's many to one from worker to manager. The many side is the side with the primary key. So worker's employee ID is going to be the primary key for that, even though we have the employee ID appear twice, because one's for the worker and one's for the manager. We would end up with something like this, right? So, since this is the case, you'll notice that both of these schemas have the same primary key, right? Can we combine them together? Now, this is an interesting question. You probably have already seen this combined together because you'll have employee ID, name, blah, 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 manager ID. You can plop that on the end, and if you want it to be optional to have a manager, you just make it nullable. Okay? So it's interesting that you can actually combine these things together. We're going to talk more about that probably next lectures when we'll talk about this whole topic of schema combination. Okay? Yeah, in fact, I'm pretty sure that is next lecture. Okay. For a degree greater than 2, well, easy enough. We do the same translation. Look at all the participating entity sets that participate in that relationship set. Take the union of all their primary keys. That becomes a super key for the relationship set. Obviously, it's necessary to describe it. If there's any descriptive attributes, you plop those in as well. Okay. If you have one arrow out of the relationship set, remember it's degree greater than 2, follow the same rule as I said before. Anything that's on a many side is part of the primary key. Okay? The only thing that's not going to be part of the primary key is the thing with the arrow to it. Because that's a thing, so it's the combination on the sides without the arrow, the combination that can only appear once. So the primary key is going to include all those guys. And we simply don't allow more than one arrow for relationship sets with more than 2 entity sets participating. Okay? All right, those are the rules. Let's see, what else do we have? Okay, so employee job branch. So again, we have this ternary relationship set. The schema for works on, well, it's got to include employee ID, title, and branch name. It's got to include all of those things in one place. Okay? These are the entity set schemas. Yeah, blah, blah, blah. So we know it's going to include employee ID, title, and branch name, but then we have to figure out what the key is to enforce, and we just look at the many sides, because remember, a combination of an employee and a branch can only correspond to one job. So we enforce that by putting a key constraint on the combination of employee ID and branch name. So that a particular employee-branch pair can only appear once in that relationship set. Okay, questions? It's easy, right? I mean, it's like, oh, okay, this all makes total sense. And it's a pretty powerful abstraction. You can do some pretty powerful things with it. Okay, last thing to talk about. This will be the last thing we discuss for today. Weak entity sets. Remember that they have to have at least one strong entity set that they're associated to through an identifying relationship. Okay, so how do we translate these? Well, they're pretty straightforward. Okay, notice weak entity set A, owned by strong entity set B. So we know the attributes of A, it's the weak entity set, and remember that some portion of those attributes has to be a discriminator. B is a strong entity set. It has a primary key. We can use our magical function to get those attributes. And so the relation schema for A, the weak entity set, notice it includes all the attributes of the weak entity set plus the key from B. Remember, just like your checks, your checking account checks are a perfect example of this. They literally illustrate this process. So primary key of A is the discriminator of A, unioned with the primary key of B. So we enforce that as a constraint. If you think about it, when you're storing bank account checks, the check number isn't unique across all checks in all accounts, but the combination of check and account number has to be unique, so you enforce the combination of those two things as a primary key. Okay. And then, of course, since this weak entity set's implementation schema is including B's primary key, we also have a foreign key from A's implementation to B, because we want to make sure those primary key values actually appear. Okay, identifying relationship is many to one. Remember that, so let me back up here, because this is kind of a big deal. This was the translation for the weak entity set. All we focused on was how to do A. We presume we already followed the rules for B. It's a strong entity set, all of its attributes go into a table. Whatever B indicated was its primary key, that goes onto the table as well. That takes care of B. Now how do we translate A? Well, we go ahead and do that. But notice that we already include B's primary key attributes in the translation for A. Since we do that, the identifying relationship is already covered. We have a foreign key constraint from A's representation to B. Well, that captures the identifying relationship. And it's many to one. So we just impose a not null constraint on B's attributes, except wait, we don't have to do that either because B's attributes were part of the primary key on A. All right? So it turns out that you don't have to do anything to capture the identifying relationship. The identifying relationship automatically gets included in the translation. All right? So everybody got that? This is our first indication that we can do clever things combining schemas. Okay? We have a weak entity set and a strong entity set and a relationship between them. We can do that translation. We don't have to worry about representing the identifying relationship because it's already captured. Okay, let me see. What else do I say? So here's basically the picture. We really simplified our account representation. But you can see our checks have a lot of junk on them. So account schema, account number, and balance. And of course, account number is the key. Check schema, well, it's going to be all the junk in the box plus accounts primary key. So we pull that across as well. So primary key is account number, check number, and we end up with something like this. And I don't say it on here, but there's a foreign key constraint from check.account number to account.account number. Everybody got it? Can you have multiple checks with the same account number? Definitely. Can you have multiple checks with the same check number in different accounts? Definitely. But a particular combination of account and check number has to be unique. Alrighty. Cool beans. Here's the other fun one. We had this example. Well, hopefully you can see exactly how we would do this. Where do you start? Well, when you're doing something like this, always start with the strong entity sets. They're easy. Just take care of the strong entity sets first. So we do student to username, assignment, short name, due date, URL. That's all easy enough. And then submission, weak entity set. Okay, so we have version. That's the discriminator. And we have two identifying entity sets this time. No biggie, we can handle that. Okay. So we just take the owning entity sets primary keys and suck them in. So we have username, short name, and version are all part of that weak entity sets representation. All right, make sense? Easy. Do we need any schemas for the identifying relationships? We don't, because that's already covered by our representation. We have 2 foreign keys as well we have to make sure we represent. Okay, composite attributes. Well, we just don't do them in the relational model. Turns out you can do them in SQL. We'll talk about that in the future. But when you're mapping composites to implementation, you just take all the components and map them. Well, that's easy enough. It's not very exciting. So if we had customers with addresses like this, well then, again, doing this in the simple, pure relational model, we just plop it down. Okay? Nothing exciting. We'll talk about how to do these kinds of data types in the future. It's a non-standard extension, though, I think. It may have been standardized recently, but many databases don't support doing composites anyway. Multi-valued attributes. These are far more interesting. Multi-valued attributes require a separate relation schema to represent the multiple values, because the relational model only supports atomic data values stored in relations. So basically, since we have this, so ER constraint on multi-valued attributes, for a particular entity, all of the values in the multi-valued thing have to be distinct. They're sets. Again, they're sets of values. So we end up with something like this: multi-valued attribute M in any set E, relation schema capital R to store M. Ooh, this is bad because R is, we frequently use that for relationship sets. But you'll just have to bear with me. Relation schema R to store M with the attributes A, so the single valued version of M. Notice what do? Well, we have the single valued version of M plus the primary key of the entity that references it. And we just have multiple rows. We have 1 row for each value in the multi-valued attribute. Okay. So this is interesting. Let me see. I think I have an example. Yeah, so customer name, we're going to allow multiple addresses. This gets kind of gross because we had the constraint that the multi-valued attribute has to be a set of values for each entity. So we would end up with something like this. Notice customer no longer has the multi-valued stuff. Customer becomes just cust ID and name. And then, of course, we have cust ID as the primary key. Since we allow multiple addresses, well, we create another relation schema with street, city, state, zip code, because that's the single valued version of the multi-valued attribute, and the primary key of the owning entities. So we have customer ID in there as well. And then everything becomes part of the key. The reason why everything is part of the key is because the multi-valued attribute is a set of values. It's not a multi-set of values. If it was a multi-set, it'd be harder to reason about. We just have customer ID be the primary key, and everything else will be left out. Okay? Any questions about that? That's going to become very important. We're going to talk about this again and again, actually. So make sure you pay attention to that. All right. So if there's no questions. All right. We'll see you next time then. We are done for the day.